I'm ready. All right, so we're having our final lecture on session types and second final of today in this summer school. So, well, thanks for sticking around. I guess those, for some of you, you had 3 weeks, so that must have been, you must be dead by the end of today. So, but believe me that also for us lecturers, we are dead by the end of the summer school. Okay, so today I would like to talk about sharing, and I'm going to speed up a notch because I'd like to present basically sharing to you because that's really recent work, whereas so far we've basically discussed the foundations. And I got also a request by one of the students to talk a little bit about what my research is about. So I'm going to do that today. And for this also, I will have to just basically only brush bang. But for those of you who are interested, I'm happy to talk about this, and I can also point you to material. So far we talked about linear session types, and there was one connective, which is exactly the bang or the of course, that we have not really integrated into our linear session type language yet. And I'm going to do that very briefly in the sense that I just want to show to you basically what do we get when we have bang incorporated into our linear session type language. And I'm not going to go into the details in terms of basically deriving, you know, basically the typing rules and their operational interpretation, because it's a lost cause for the purpose of this lecture for me. I'll just summarize it and tell you what the result is, and then we go from there. All right. So, but just to remind you, let's see where I'm at here. Right. So, when we looked at our let me write down basically the abstract syntax of linear session types. So we've seen channel output, then we've seen channel input. We also saw external choice, which when we have like the generalized version where we have n labels, looks like this. Then we have internal choice, the dual of it. And then there is basically this one connective bang A, or of course A, that we haven't looked at yet. And there are also judgmental rules that come with it. So what is the semantics of bang A? It's a way for us to introduce persistent truth into the language, which means that we are going to, if we are going to integrate that into our language, we are going to extend our typing judgment. So far our typing judgment was to type a process term P relative to a linear context that contained all linear channels. So that was our typing judgment so far. And once we introduce persistent truth into our language, we get an additional context, which I'm going to refer to as psi. Paul, in the first week, he used gamma, but I have a reason why I'm not going to use gamma for this. But, you know, we can use whatever, basically, whatever Greek letter we want for it. But sometimes there are some conventions. All right, so just to be explicit about this is a linear context, and the psi is going to be a structural context. So by structural, I mean it's an unrestricted context, meaning that it has all the structure rules, which means it also has weakening and contraction. And weakening and contraction are exactly the rules that we reject for delta. Okay, so far so good. Also, let me point out that we have judgmental rules. So we have an analogous thing for cut, which is cut bang. I think actually we usually write it like that. And then we also have a copy rule. And we have left and right rules for bang. So we have bang right and bang left. And all those rules have an operational interpretation, in terms of the pi calculus. So rather than showing you the rules now out of time, I'm going to skip that. But I'll show you what bang corresponds to in the pi calculus and what it means operationally for our language if we were to integrate that. So bang corresponds to process replication in the pi calculus. And interestingly, in the pi calculus too, you come actually across, also the bang is used in order to replicate the process. So in the pi calculus, usually bang is not a reduction rule, but it's actually defined by structural congruence. I'm just throwing this out there. But what it means is essentially that we can always expand. So this is structurally congruent to a process, basically a copy of the process that runs in parallel with the replicated process. So let's think in terms of a picture. So what does that mean in terms of the process calculus? I'm going over here now. So let's assume that we have a process Q that is, or maybe I'm not, yeah, okay, I'll write it inside. And this process is now connected to a bang P. And notationally, I'm just, that's me now for the purpose of this presentation. I'm going to denote this by a double circle, okay, so that we can easily identify that. And let's assume that they are connected via a channel U. So operationally, what we get, in particular by applying the copy rule, we can do the following. The client Q can send to P a new channel. So it sends along U a new channel X. And then as a result of this, we get the following picture. So we have now Q running, and Q is still connected via the channel U to the replication process or replicating process P, bang, along channel U. But now in addition, so upon receiving a fresh channel from Q, the replicating process does the following. It creates a copy of itself, spawns it in parallel so that it runs in parallel, and makes sure that that process offers along the fresh channel X that it received from Q. So we get the following picture. So that's what we operationally get when we introduce persistence truth. So it's replication. So in particular, we we get a copying semantics, right? So let me write that on top of here. So now we got, as a result of sending a fresh channel, we now can interact with a copy of P along that channel X. So the sole purpose of basically this replicate, that you can think of this as a server, that the sole purpose of this server is to provide you copy of the process P. Okay, so my main point in basically going into this is to explain to you that this is certainly a valuable construct, but it depends on your specific application scenario. If you actually do not want a copy of a process, but rather share the process with other processes, with other clients, then this is not the right construct. So think, for example, of this P being our queue. And we want to have multiple consumers and producers that interact with that queue. So obviously by using bang, we don't get what we need. Because why? Because if by using the bang, I now get a copy of the queue, and now I can interact with that queue. And let's say there's another client that also requests a copy from P. So now this other client has its own copy of the queue. We don't get any sharing of so the two clients do not affect each other. So we actually are not sharing the same queue. All right, so that's now where basically manifest sharing comes into place. So let me maybe write that down. So, so we could have, in particular, we can have the following scenario where we have a client 1 and a client 2, and they both are connected to the replicating server process bang P along channel U. So they basically share this channel. But whenever they try to obtain a queue in order to interact with the queue, to store things in the queue, retrieve things from the queue, they get their own copy. So we get something like this. So C1 has its own copy, and C2 has its own copy. So whatever C2 does on its own copy is not going to affect P over here and vice versa. Okay, so that's all I wanted to say about this, because now that nicely paves the way to what we are going to talk about today, which is sharing. So we have, we started working on this problem because just by the observation that essentially there are real-world scenarios that cannot be accommodated only with linear session types and persistent truth alone. And so we were trying to find a way to somehow integrate sharing, but in a logically motivated way, so that we do not destroy the good properties that we get from linear logic. So, and our work has resulted in what we call manifest sharing. And the name manifest will be, the term will become clear later. And that's actually work by myself and Frank Pfenning. That was published last year at ICFP. And that's what I would like to talk about today. And I hope that I can, so essentially I want you to get the main ideas so that if you are interested, you can go ahead and read the paper. So, the scenario that we want to accommodate with manifest sharing is the following. So the scenario of a multi-producer consumer queue. So over here, I'm just right now writing down one consumer, one producer, but there can be many. So we have a consumer here. And here we have a producer. And then for those of you, yesterday we looked into the implementation of the queue, right? And we used the element and the empty process. So now I can actually write that down. So the head node of the queue is an element process. The next one, 2. This one, 2. And the last one is an empty process. That's the one we've written together yesterday. All right. So we're basically, can you see that now I basically brought you back to the state where we started in? Because I already wrote down a picture like that in the first lecture. And we both discovered, we all together discovered that that's really a challenge for
preservation.
Exactly, preservation. So now I tell you, let's do it. And earlier I spent 3 lectures explaining to you that, well, we'd better not do that. But as I've motivated just now, there are real-world scenarios where we need it. For example, I'm working with the Rust people, or the server people at Mozilla Research, and basically they use message passing concurrency, and they're interested in using session types to basically express the message passing concurrent programs they write. And the programs they write, they need sharing. So let's try to understand that. So what do we do with preservation? Okay, so now let's move this up. I'll go. All right, so what did linearity give us? Well, linearity made sure that we have exactly one client for each provider, right? That's what we got. And that kind of made sure that each client interacts with the queue or the process, the providing process, basically in isolation of anyone else, right? So it's when the client interacts with the queue, it is guaranteed there's no one else that's going to mess around with the queue. All right, so can we use another concept to basically achieve the same thing? Do you have any ideas? Okay, so what we could do is we basically could have the several clients, but how about we just make sure, rather than insisting that there is only one, we insist that they communicate with the queue in mutual exclusion. Then at least when one client interacts with the queue, the client is guaranteed that there's no other one that also messes around with the queue. Okay, so let's go with that idea and push that a little bit further. So what we are going to do is, so now I need all my colors, I So we are going to introduce the notion of a shared channel and linear channel. So we allow there to exist shared channels in addition to the linear channels. But then we want to make sure that a shared channel, before we can communicate along the shared channel by enqueuing and dequeuing things in the queue, we first have to make sure that we have exclusive access to that queue. So we introduced the idea or the notion of acquiring the channel. Once we have acquired that channel, it becomes de facto a linear channel. Then we can go ahead and communicate with the queue. And if we are done interacting with the queue, we release the channel, at which point it becomes shared again. So let's draw a picture. I'll bring this over here, my colors. So we have this scenario. We have the producer and the consumer, and then here we have the head of the queue. And now, when we start out, they're all connected by shared channels. And I'm going to use red for the shared channel. And additionally, I'm going to make them dotted. Okay, so that's channel Q. And then we have the channels connecting the remainder of the queue. All right, so that's how we start out. So at this point, neither can send enqueue or dequeue messages to the queue. So that's our consumer. Oops, I messed it up. Or what did I have? Yeah, I have had consumer on the top. And that's our producer. So when they're connected to the queue via shared channel, they cannot interact using the linear connectives because the channel is shared. The channel has to be linear in order to interact with the queue as we have defined it so far. But what they can do is they can acquire the queue. So let's assume that the consumer goes ahead and says, "Hey queue, I'd like to talk to you. Please give me unique access." So it sends an acquire request. Well, if the queue is available, and in this picture it looks like it is the case because it's not interacting with anyone else, then as a result of this, the client actually, so the consumer will get a linear channel. And I'm going to use blue for the linear channel. And note that the producer actually still has only a shared channel to the queue. And once the linear connection, the linear channel is established, the consumer can go ahead and exchange messages according to the queue protocol we have seen so far. So the consumer can enqueue and dequeue things in the queue. Once the consumer is done with interacting with the queue, it's going to send a release request Once that release request is granted, it gets back a shared channel. Okay. So what happens? So far so good, right? Or are there any questions up to here? All right, so that's the basic working. Yeah, question.
Instead of doing this, we can add this functionality in processor itself, right? Because process have empty and another one is non-empty.
Yeah.
So when two consumer and producer are trying to communicate at the same time, this functionality could be added in the processor itself.
Right. So we could, absolutely right. We could basically encode this working in a methodological style, right? However, what we're aiming at is to lift this up to the type level, and I'm getting to that. So rather than having programmers rely on adopting an acquire-release discipline programmatically or in terms of a methodology, we actually want to make sure that our type system makes guarantees that this is the case. Very good question. So just hang in there and we'll get there. All right. Another thing I want to point out is the following. What happens if both the consumer and the producer try to acquire the cue at the same time? Well, just one will get it, right? And the other one will wait until it's ready. The reason why I point that out is because this is now our source of non-determinism in the language. So it will be non-deterministically chosen which one of the two will get access. That also makes clear now that we don't have this form of non-determinism in a linear setting. In a linear setting, everything is deterministic. And that's one reason why I wanted to talk to you about sharing, is because we're talking about concurrent programming. All right, so that also is a reason, because we now have non-determinism and we have n-ary channels, so the possibility that several clients are connected to the same process. That's the reason why now we are able to simulate the pi calculus in this language. In a linear setting, we are not. Okay. So now I'd like to address your question. So far, this is just basically a programmatic working, right? Or a programmatic discipline. But we're doing types. So the question then becomes, what is the type? So here this channel, or I should actually use the red again, right? So that's our channel Q. So the question now becomes, what's the type of Q? But it cannot be external choice of something, right? Because that's the type of the Q once it is linear. So we have to somehow enrich our type structure with the notion of shared session types, right? So, but before doing this, let's briefly look at the Q protocol that we used so far, right? So we defined that a Q, we had the following session type. Q of A, so we have a polymorphic Q that basically stores elements of type A. And we defined it to be as to be an external choice of an NQ where we get a channel input, and then after this we release, recurse as a Q, or we are willing to receive a DQ, at which point we indicate whether we are empty or not empty. When we are empty, what I'm going to do now, earlier we terminated here, but since I want to use, right now I write down the linear session type, but eventually I want to move into the direction where this is going to be a shared session type. So in here it doesn't make sense to terminate the queue when it's empty. So I'm actually going to recurse here too. Or it is not empty, and then we send a channel, and then again we recurse. Okay, so that was our linear session type so far, right? So let's think about it now. So now that basically we switch, we go back and forth between linear and shared channels. So what does that mean for the type? It means, and also for the process itself, it means that the process can go through phases. At some point in the protocol it's shared, and then once someone acquires access, it becomes linear. And then once the client that has unique access now decides to release the queue, it becomes shared again. So let's denote that by coloring parts here. So certainly we want any of those interactions to be linear, right? So I'm going to basically underline them. Right? Also the DQ, they should all be linear, and also they should be linear. But at the outset, we want the queue to be shared, right? Because we want it there to be possible that several consumers and producers can interact with the queue. So essentially the queue should be shared. So I'm going to use red, which means also when we recurse, we go back to a shared queue. So now you tell me where in the session type, at which point should a client request an acquire or release? At which point should a client request an acquire? Before doing any of the things, right? So essentially, let's use red again. The acquire should happen here. And the release should happen before we go back, right? Before we recurse. So that means the release should be, or let's actually use green for it, because then, why not? All right. So before we recurse at the share queue, we have to release, and also the same here, and also the same here. Okay, so what can we see? We can see that operationally, processes and channels become phased. We can distinguish a linear from a shared phase. And the process goes back and forth between those two modes. And we can also see that even though we haven't changed our type system yet, but we can see that there's a way for us to reflect that phasing also as part of the type. Right? Good. So let's do that. So far we only had linear types. So let's expand our type system and introduce shared types in addition. All right, so what we're going to do is we are going to say, well, our session types, there are basically two different kinds. There are those that are shared, and I use a subscript S to basically indicate the types that are shared. And in here we are going to put some connectives. And then there is the layer of linear session types. And I'm going to use the subscript L to denote those. What kind of connectives am I going to put in here in the linear layer? Yeah. The ones over there, exactly. So let's do that. So we have internal choice. Well, that's not a nice curly brace, so let me do that again. I'm going to arrange it slightly differently, so I basically split them by polarity. So I first have the positive connectives. Oh, and that should be subscript L. Then we have, so here we have internal choice. Here we have channel output. Then we also have termination. In addition, then here we have the negative connectives. So external choice. Then we have channel input. So A sub L, lolly, B sub L. All right. So that's basically what we already had, right? Oh, I actually forgot termination up here. Sorry. And because we are now get real sharing, we don't bother about the bang. However, I would like to point out that that's kind of an orthogonal concept, and we could easily also integrate that and have it as part of the linear layer. But in order to keep things simple, I'm not going to do that. But that's a possibility, which would then give us copying semantics and sharing semantics in one language. Okay? So, these are the connectives we have so far. So now the question is, well, we're not yet quite there, right? I put down this shared layer, but I didn't put anything in it. And just think about this for a moment. I mean, essentially, at least we need two connectives, right? Two more connectives, because we've just added earlier two new language constructs, which are acquire and release. Yes. Okay, you're tagging along. That's amazing. Good. So we need to have new connectives that represent the acquire and the release. Okay, so now let's think about this. What does an acquire do? And let's look at this session type, and let's look at the color coding also, right? The acquire, before the acquire, the providing process is shared. After the acquire, it becomes linear, it's blue. So somehow all the acquire really does is it takes us from one layer to the other one. It takes us from red to blue, right? So what does the release do? And now there's no real surprise, right? So far all the connectives we've seen, they're always kind of inverse to each other, they're duals. So what does the release do? It goes the other way around, right? It takes us from blue to red, from linear to shared. Okay, so now we can use basically ideas from a adjoint formulation of logic, and we can express the acquire release as modalities, as so-called shifts. So let's do that. So the acquire, we can express it as an up arrow, meaning that it takes us from the linear layer, which I write here as a subscript, to the shared layer. So the way how to read this is we take a proposition that is at the linear level and shift it up to the shared level, which means the entire thing is now shared. And we can do this with any linear session type. So note that in terms of the coloring, it's like follows. So here we have, oh no, wrong color. You know, I would like to have like a mega marker. I would have to so that I don't have to underline things, but that's not yet available for whiteboards. Okay, so this is a linear proposition, linear session type. And now the arrow takes this linear one and returns a shared proposition. So the result at the outset, this entire proposition is shared. That's why it is in the shared layer. Okay. Then here, these are all linear propositions. So that means we also need the down arrow. Good. Let's do that. So we get an additional connective. We get a down arrow that takes us from the shared to the linear layer, and it does that to a shared proposition. I'm going again to highlight this here. So here we can see this guy is a shared proposition, but because we prepend a down arrow to it, the result is a linear proposition. So now we have a stratified formulation of our session types. And for those of you who are interested, so this kind of adjoint formulation, we can actually generalize. So we could add another layer, which is, for example, affine. And then we can have like a universal or unifying way of dealing with the different structural properties and propositions that we have. But that's just a side remark. I'm just pointing out that this idea can be generalized to some extent. Also, I would like to point out that for the system to basically to maintain the good properties of the system, we basically set up an ordering between those layers. So the idea is essentially that this layer, the shared layer, is basically higher up in the hierarchy, if you want, than the linear layer. And in particular, what that means is that when we type a shared proposition, it cannot rely on something that is lower in the hierarchy. But the other way around, that's admissible. And this will become clear when we look at the typing judgment. But the reason for this is basically because one layer, the structural layer, has more structural properties. So if it were to rely on linear properties, it's not aware that weakening and contraction are not admissible. So it might actually mess around with those resources. So that's why a shared proposition cannot rely on any linear resources. But the other way is possible. It'll become clear later when we look at the typing judgment. But I just want to point out that the layering also goes hand in hand with the hierarchy. All right, so let's go back to our session type. Now we have those connectives. So now let's discover where are we going to, how can we now make this session type fit our new type structure? So far I had those things which were basically, I just put that in order for us to derive the layering, but I have to end up using real connectives here, right? So we have to place the shifts, right? The down and the up arrows. Okay, so let's do that. Any suggestions? What am I going to put in here? It's up arrow. You said up arrow, right? Because only that way. So this is a linear proposition, but at the outset, it has to be a shared one, right? QA is shared. So we have here an up arrow. But now, in all other places, we have the down arrow, right? Because here we can also see, like the down arrow takes, at the outset it's linear, but inside it's shared. So here we get all down arrows. All right. And now we have our session type. However, there's one little thing I have to tell you. So, well, because of our independence principle, so that we require that a shared process cannot rely on any linear resources, we are now requested that we can only store shared resources inside the queue. Of course, again, we can acquire and release those and they become linear. But just when we define the queue, inside the queue, we actually can only store, so the A's actually have to be of type A sub S. Which means that we can no longer use tensor and lolly here because they are for linear channel input and output. So what we are going to do is we need two more constructs. We need the ability to send and receive shared channels along a linear channel. So we get basically constructs of mixed mode, which are going to be those ones. For a shared channel output, we use the existential. So it allows us to send a channel of type A sub S and continue as a session of type B sub L. So it's a linear, so it's still at the linear mode. It's just that we receive or send a shared channel. And then also down here, we use, for the input, we use pi So that's for an input of a shared channel A sub S, and we continue as a linear channel of B sub L, which now means also here we are going to use pi and then we continue as the Q, and here we are going to use exists. And we continue as the Q. All right, and now we have our shared session type Q. Yeah?
I think it's one acquired and 3 release.
Sorry?
One acquired and 3 release. We have for every.
Oh, right. So the observation was we seem to have 1 acquire and 3 releases, right? Well, that's a good question. So it doesn't mean that that's always the case, that we have 1 acquire and 3 releases or whatever. It's dependent on the structure of the session type. Whereas I will say that later on we are going to kind of restrict that a little bit, and I get back to this. But in general, it's the protocol that determines where we want to acquire and release. And so typically when you play with session types, as soon as you have choices, there are several branches. So it's quite natural that at the outset we have an acquire, and then within for each branch we have a release. So the fact that we have 1 acquire and 3 releases here has to do with the fact that we have an internal choice nested into an did I say it right? We have an internal choice nested in an external choice, sorry. So the external choice gives us 2 branches, which basically says that there are going to be 2 releases. But in one of the branches, we have an internal choice nested, which also has 2, so we get 3 releases in total. Okay, so it really depends on what protocol you are defining. And as soon as you have choices, it's quite natural that there are more releases than acquires, because you acquire the entire thing at the outset. And then for each choice, there's basically a branch you take. Okay? Yeah?
What happens if you don't release it in the signature? Like for example, let's say what happens if, for the case of none in the queue, you just terminate, then does it violate anything?
All right, very good question. So the question was, what happens if in one of the branches I don't release? Well, what you get is that you hold that lock conceptually on the queue forever.
But shouldn't the type prevent that from happening?
We'll get back to that. Right. All right, so good question. So hold that thought, and I'll get back to it. All right. So next thing I want to do is I want to derive the typing rules with you. And then we get back to your question. You're kind of 2 steps ahead. All right, so but first, let's try and figure. So I'm actually going just to pull that up. That should be fine. Yeah, that's actually, my board management is really good, but just happens to turn out that way. All right, so the typing judgment we had over here without the bang, right? We just have a linear context. So you can imagine, right? We are going to end up having something similar like over here where we added bang. So in particular, in order to type a linear process, let me actually write this over here. So to type a linear process, we are going to have the following judgment. I now use gamma for the context where I have all the shared channels. And I use gamma rather than psi because those guys have a sharing semantics, whereas the psi here is also structural context, but we have a copying semantics operationally. Okay, so we have here gamma, we have delta, and so we type a process P relative to those contexts. And now, basically, this process offers along a linear channel, X sub L, a session of type A sub L, a linear session. All right. So to type a shared process, we have the following judgment. We type it relative to the shared channels. It offers a session of type A sub S along a shared channel X sub S. So note, that's exactly what I pointed out earlier. There's a hierarchy imposed on the layering which prevents something higher up in the hierarchy to rely on something that is lower in the hierarchy. And that's exactly the case for the shared processes here. And the reason is because there are different, the contexts have different properties. So delta is a linear context as we had it before. And gamma is a structural context. So with a sharing semantics. So this means in particular we do have weakening and we do have contraction. Whereas we do not have weakening and contraction over here. And we need weakening and contraction in the structural context, otherwise we could not have the scenario up there where we have both a consumer and a producer that are connected via a shared channel to the queue. So in other terms, in more programming terms, what do we get now? What do we introduce into the system? So far we only had linear references, right? Linear channels, linear references. So there was only always like a unique other guy on the end. What do we get now? It has a fancy term in object-oriented programming. Yeah?
Well, I was going to suggest a directed acyclic graph. But
I wish it were the case. No, we get aliasing. Right? We have aliasing at work. It's just, we use here channels, but it's semantically, we get aliases. And along with it, all the troubles if we are not careful. All right. So now let's go with typing the acquire. Right? So let's do that. So obviously, to type the acquire, we have our gamma, and because we acquire a shared process that offers along a shared channel, we must have a shared channel, right, in our gamma. So we have here, along X sub S, we have an offer of a shared session type. So what's a shared session type? The only shared session type we have is of up arrow something, right? So that means this X sub S has to be of up arrow that takes L to S of a linear session of type A sub L, right? Then also we are going to have some linear resources, and our process term is the following. I'll write it down and then I'll read it to you. What did I use here? All right. Okay, our process term is the following. We are trying to acquire the process that offers behind or along the shared channel X sub S. If we are successful, we get back a linear channel that I refer to as X sub L. And then after that, we continue with our continuation queue that now binds X sub L. Okay, and so we are left rule. So by doing this, we do not change our offering type. So, which becomes apparent once we write the premise. Okay, so you tell me. So obviously here, we are not going to change our offer, right? Because we interact, it's a left rule, so we interact with something we are a client of. All right. So, what am I going to write over here? And clearly in terms of the process term, we are now executing X sub L, right? Right. So what happens here? What do we have in our shared context?
Everything except Excel.
Everything? What is?
Yeah, with Excel.
With?
Yeah.
Right. We still have the X sub S. And now you can see contraction at work. Right? We have context. So now you can see really the interplay between, or the different semantics of what it means having contraction set up for one context but not for the other. So we'll see that when we look at the typing rules. I'm just pointing it out. Please bear with me. So now we also have a delta here. And what else am I going to write? If our inquiry is successful, we get back a linear reference, right? A linear channel. So where does it go? We have it now in our delta, right? Good. So I have an X sub L in my delta. Of what type is that thing? A sub L, right? All right. That's our rule. No surprises really, except knowing what it means to have a structural and a linear context around, and what the stratification is, and so on. Okay, so far, I've only up to this point, I only talked about acquire and releases, right? And release would basically do the other thing. However, we have also write rules. So I have a little bit lied to you so far because I've only talked about the left rules. Both acquire and releases are from the point of view of the client that interacts with the process. But we also have to define what, in this case, up arrow means from the point of view of the provider. Right? So we have to define the right rule. So let's look at that. So, well, let's start over here, and maybe let me just draw this. So I have the up arrow LS, right? That's the rule that we are going to write. And, well, in what state will the provider start out? Something that can be acquired. Is it linear or shared? It's shared. All right. So that means it's going to have a gamma, right? And maybe something here we don't know yet. Turnstile, the process term, and then over here, it's going to offer something. And we've already figured that what it is going to offer, it is going to be of a shared type, which means it's something of up arrow, right? So it's offering something of up arrow A sub L. Okay, so, well, since it's really working only on the right side, there's nothing over here, it's just the gamma. Now we have to come up with a nice process term for this. And the one we've chosen is the following. accept an acquire request from the client. That means, so we accept the request of an acquire coming in along X of S, and as a result, we henceforth offer along a linear channel X of L. Okay, so what does that mean? So above the rule, what are we going to offer now after that we have accepted an acquire? So we started out as a shared process and we accepted an acquire request by the client. What are we now? Linear, right. So now you can really see how that works. Processes go back and forth between two modes. They go back and forth between linear and shared. So that means here, we're now offering along an X of L and a session of type A sub L. And oops, I forgot here the continuation. I apologize about that. Right? So now we execute our continuation in which we bind the X sub L. And we continue with gamma. Now that we are linear, we are going to have a delta. What is that delta? What kind of, does it contain any channels yet or not? Nothing, right? Because we've been linear so far, shared so far. As a shared process, we do not have any linear channels. So we start out with an empty linear context. But now that we're linear, we can acquire other things. So we can populate this linear context. Okay, so let's move on to release. Now you're almost pros, so you already know what to expect. So for a release, we have here a gamma and a delta. And because we are releasing something, it means that we have a linear resource that we want to release, right? So we do have an X sub L that is of a linear type that we can release. What type is this X sub L? Just have a glance at our types. It's a down arrow, exactly. It's a down arrow from S to L of A sub S. And then the process term, we say, okay, I write it down. What did I use? We continue as a All right, so that's our typing rule for down arrow left. So we release the linear channel X sub L, and then as a result, we get back a channel, a shared channel. So now let's figure out what the continuation will be. So in our continuation, well, we'll get a new shared channel, right, as part of the release. So that means we are going to have a channel X sub S of type A sub S. And A sub S will be something of up arrow, right? And then we're going to have our delta. What about the X sub L? Are we still having this as part in our continuation? So so we are now typing the Q X sub S. We'll get this. What about the X sub L with releasing? Yeah. down because of linearity. That's the whole idea. When we release something, we give up exclusive access and we give up the linear reference that we had. If it weren't for that, our whole methodology would break down. Because if the client that releases a resource that it had linear access to continues having linear access to that queue, then, or that resource, then everything would break down. Okay, so let's finally look at the right group for the down arrow. Okay, so obviously, what are we going to offer? Something that can be released is right now what? Linear or shared? Something that can be released is right now linear, right? So it's X sub L of type down arrow A sub S. Once it will have been released, of what, in which phase will it be? Shared, exactly. So it's going to offer something along now, a shared channel of type A sub S. All right, so so it certainly has a gamma. It's right now linear, so it has a delta. We'll get back to that. So let's write down the process term. So what it shows is we have to have an antagonist basically to the release, right? So what we do is the following, and I explain that. I provide you with intuition, okay? Or the thing that we thought about when we came up with this. All right, so the idea is that we can initiate a release by detaching ourselves, and that's how then the client can do the release. So a provider detaches itself, and then the client can do the release. All right, so the question is, what about any linear resources? And let's maybe finish up here. So as a result, we get the shared process that then will just execute this continuation P. So, are we allowed to have any linear resources before we become shared? No, exactly. So linearity really requires us to consume everything before we detach ourselves. And this is analogous also to termination, right? When before we close, we have to consume up all the resources. So this is exactly the same idea. Okay. Yeah.
So for the down arrow left, shouldn't the XS appear in the gamma below as well?
Can you say that again? For down arrow left.
Shouldn't the XS, the shared channel, appear in the gamma because it's always there?
Yes, that's a very good point. It could already be in gamma. Exactly. But since I start out with the gamma, so I'm just adding it. If it's already in there, so I can actually have several occurrences in the gamma because it's a structural context. That's right. For the linear context, it's not the case. Very good question. All right. So now I'm also getting back to your, Suarez, I'm getting back to your question you had initially. So let's basically take stock here. So we have, what we did so far is we enriched our typing. We have a stratified system of types now. We have a programming discipline of acquire-release, which is cast into the type system, which means type checking ensures that we adopt acquire-release, that we adhere to this discipline, right? If the program type checks, we are ensured that we never messed around when we dealt with resources. There was always one owner at the time. So that's that guaranteed preservation. And that goes back to your question. I think so, at least. I think you thought a step ahead. Do we get preservation? Okay, so let me say, unfortunately not. There is one thing missing. So it's true, while we interact with the queue, we're the only one. So we know that when we enqueue something, that the next thing we can do is that we can send something, right? So as long as we interact with the queue, we're good, we get preservation. However, what if I acquire the queue, work with it, and then release it? And I release it back at the type which we indicate, right? Once it's back to queue, I release it. What if someone of you acquires the queue, and let's think that the type is not as it is right now, and it releases the queue at a different spot. It releases the queue when one should actually send something, enqueue something. Well, okay, so one of you did this, releases the queue, and now I want to go ahead and interact with the queue again, and I believe that it's queue, so I can enqueue something. Well, it will fail, right? We get a failure of preservation, because we are not coordinated in the way how we interact, at which point we acquire and release the queue. All right, to get preservation working, what we need is, we need to impose a well-formed risk condition on the session type. And this well-formed condition is actually, that holds true for the session type we wrote up there, right? This well-formed risk condition tells us that if I acquire a shared resource, whenever I'm going to release that shared resource, or that linear resource, I have to release it back to the same type at which I acquired it. And that's actually true up here, right? So we acquired the queue when it was at type up arrow queue. So we acquired it when it was at type Q. And we release it also back to Q. So that's how preservation will be guaranteed. So this well-formed condition we call write it down here. Or session types. And that condition we call equisynchronizing. So they basically have to be, it's kind of like the idea of equi-recursive types. So you have to synchronize always back to the same type. So that's the idea. So if we have acquire release reflected as part of the typing with the up and down arrows, plus the well-formed condition on the session type that it has to be equisynchronizing, then we get preservation. So now you might wonder, and also I want to point something out, right? If it weren't for this, we could do like some runtime checking, right? We could always, upon an acquire, we could do a runtime check to make sure that the resources of the expected type. But of course, it's much nicer to impose that condition and then get it statically. And actually, you might wonder how restricted this is. Actually, it's all the examples that you can basically think of usually follow this pattern. There are some some examples we looked at where we have to slightly relax that condition, but we can do so if we introduce subtyping into the type system. Another thing now, or there was a question.
No, I just feel like the whole thing looks like you can think of the mu type in the lambda calculus with recursion. So the mu type and with linearity at the type level, can we think of it like that?
Yeah, I think your observation is correct. There seems to be a connection to recursive types. Yes. But it's also possible, so it's not necessary that we always recurse. We could also terminate. And that would also be equisynchronizing. Yeah. But I have a remark on that in offline. So now you might wonder, what about progress? So the thing is the following, that we get preservation, but with sharing, if we do not add anything more to the type system, we get a weaker form of progress. In particular, it is now possible to have cycles. Because gamma is a structural context, it is possible for a process to obtain a shared reference onto itself. Because it's a structural context. I mean, those references, I told you, we're back into aliasing. So a process can have now a shared reference onto itself. So now imagine that process, now of course process doesn't know about it, right? It's just a variable. So the process is right now linear, and now it tries to acquire itself. It's going to wait forever. So that's the simplest version of the deadlock. But there are also other forms of deadlocks that can arise because our process graph, the arrows the green arrows I drew like yesterday on the board, there are now green arrows, another kind of arrows that arise from processes trying to acquire something that someone else holds, and transitively that guy is waiting for ourselves to, for example, to synchronize. All right. So in the language as we have it now, we get a weaker statement of progress that has to permit for a process to be blocking. And as part of my current work, I'm looking into this and I'm trying to get rid of the deadlocks. That's ongoing work. Deadlock is a very, very tricky problem. What I want to point out is now that we have sharing, we are back in the full-blown pipe calculus. And also in pipe calculus, we deal with those problems. So we are really back in a concurrent language. And that's also the reason, for example, with shared channels, we can encode dining philosophers. In a linear session type setting, there's no way even to do dining philosophers. And of course, you can do like a locking up methodology that you would use in concurrent programming with locks in order to avoid that. It's like Dijkstra basically within his initial description. Okay, so two last things as a kind of wrapping up I want to point out. So that's essentially a reference. I told you that we are now back, as I kind of like to phrase it, into the full-blown pi calculus with all its expressiveness, but also all the issues. And that's actually a theoretical result that we have proved. So there's, so we have, I want to use a black one. So we have a paper. It's just going to be presented in September at Concurrent. And that's basically provides an encoding of the asynchronous untyped pi calculus into the language that I described here.
So basically into shared session types. Let's put it that way. Or shared session type process calculus. Okay. And also what that basically shows, I mean indirectly, because you know that in the beginning I told you that Milner provided an encoding of the lambda calculus into the pi calculus. That proves sort of universality, so indirectly we've done the same thing by providing an encoding of the pi calculus into our language. So the other thing, the thing I want to conclude with is basically what does this mean now for the Curry-Howard correspondence that we set up between the intuitionistic linear logic and the session type process calculus. All right, so we had the following correspondence. So we had that, I have to use a different pen. So we had that linear propositions correspond to session types. And we had that proofs correspond to processes. And earlier we have that basically cut reduction corresponds to communication. And now what we get is basically an interleaving of proof construction, deconstruction, and reduction. So we have here an interleaving of proof construction of proof reduction and proof deconstruction. And that corresponds, the construction corresponds over here to an acquire. The reduction corresponds, so that's basically cut reduction, that corresponds to communication, and the deconstruction to a release. And basically a deadlock is a failure of proof construction. So that means we are not able to construct a proof. Okay, so that's basically how we can close the circle and try to give some logical explanation of what is going on here. Okay, and that concludes my lecture.